is that one that yeah, okay. So it is about design and engineering of EPC projects. So we will talk about what is EPC. So like engineering, procurement, and construction phases, different phases, and we will focus on various aspects of this. And like this is our agenda: introduction to EPC project management, and then we will talk about the project management workflow. So what are the various phases during workflow, and what are the documents we will issue, and what is the purpose of those documents issuance, and then workflow of engineering, procurement, and of course construction we will cover a little bit in the end, and the concept at the end, how it will be executed at the site. So in the introduction, I can say that engineering, procurement, and construction is the full form of EPC projects, and which is used for the engineering. So engineering is the basic engineering or detail engineering. And then those documents will be used for the procurement. And then after procurement, we can do the constructions. And during engineering, we can make the documents for procurement as well as for the construction, so that the layout and all those things will be useful for the person, those who will be erecting and installing the equipment and doing the commissioning. So if a company, they want to have a project, then they have to go for these phases. So in these different phases, what happens, we will see. For example, if someone wants to start an industry, so that will be from a grassroots. So then there are two aspects. They can go with front-end engineering and design feed, that is done by a specialist EPC contractor, one of the EPC contractors they will call, and then they will say, okay, hey guy, I want to construct a plant of so and so type, like oil and gas or any other plant, chemical or sulfuric acid or any other plant. So what they will say, they will call the one of the EPC conductors, and they will ask them to make the layout, and they will say that this is my plot plan, this is the area. So those people will make the preliminary document or basic engineering. So the engineering construction contractor will carry out the detail engineering design of the project, but before that one, they will do the basic engineering. So the basic engineering is nothing but a front-end engineering and design. So under a EPC contractor, that can be done, and that those things, those documents, those are will be preliminary. We can say 40% of basic engineering, like plot plan and some sort of budgetary quotations will be taken, and estimation, rough estimation will be done, and that will be floated as an inquiry to the various vendors as a complete EPC contractor inquiry. So for that one, those people will be bidding for the detail engineering. That is one aspect of the project. In this case, the contractor means the owner doesn't know. So he will call one of the EPC contractors, and he will say that, okay, I want to, hey guy, I want to have one plant of this type. So you do the basic engineering. So they will do the basic engineering, and then that will be floated at an inquiry with a estimated budget. For example, if we have to construct a house, what we will do, we will call one of the contractors or one mason, and then we will ask them, okay, I want to build a home of G+1 ground plus one floor, and then what will be the estimation? He will just have a rough calculation, and he will say the cement cost will be this much, steel cost will be this much, and this will be costing around 70 lakhs. So then I will have an idea, and he will just give a preliminary diagram, and that will be a basis for me to float as an inquiry. So that is the first phase, we can say feed. And then if we see the details of these, then we can categorize, means we just broadly we can categorize them into three: EPCM. So EPCM, the scope will be engineering, procurement, construction management. So in this case, EPC contractor is not directly involved in the construction, but is responsible for administering the construction contract. So he will do the engineering, procurement, but he will not do the construction. He will just be doing the management at the construction. So whatever they have done the engineering, so they will ensure that the construction contractor is doing the same thing what they have designed it. The next term we can say EPCI. So this is nothing but EPC, engineering, procurement, construction, and installation. So installation is also in their scope. So as proposed an EPC contractor, the offshore, this generally will be done for the offshore, and everything will be transferred at the site and installed at that location only, because offshore you cannot make it here and go there. So you have to do everything construction there itself. So this is second form we can say. And the third type we can categorize them in EPIC, that stands for engineering procurement, installation and commissioning. So everything is in the contractor's scope. So what he has to do, he has to do the engineering, he has to do the procurement, make the metal requisition, do the technical bid evaluation. All these terms we will come across. I will show the examples. And then making the drawings or documents required for the construction or installation at site. So this is called a lump sum contractor. So it is a lump sum turnkey, LSTK we call it. So this is a term which will be generally used for the scope. So there can be three scopes of an EPC contractor. So EPC contractor can play any one of these roles. And if you see the life cycle, which I was going ahead a little bit very fast, that's what actually I wanted to just show you the details. Like what I told in the beginning, that an engineering phase will include the basic engineering and detail engineering. Basic engineering, as I said, front-end engineering design. For example, there is nothing. The contractor has to do everything from the beginning, from the scratch. So the process engineer will do some sort of software calculations, and they will make process flow diagram and the roughly estimated PNID, and the instrumentation people will make the MTO, and piping people will make the MTO, and then civil people will make the MTO, and some sort of budgetary quotations will be taken, and broadly a rough calculations will be done, and a rough estimation of the project will be done in the basic engineering. That will be an input for the detail engineering. So in the detail engineering phase, once the contractor is given order only for detail engineering, then he has to carry out further. So because the basic preliminary plot plan will be there with them, and then they will have the basic index, instrument index, like for example, PNID, process flow diagram, and basic some sort of civil MTO will be there, and piping MTO, material takeoff, on all the list, broadly it will be there. It will not be in detail. But once they will do the detail, and they will have to recheck those things, and they have to correct it, and then they have to make it in a detail engineering. So those engineering documents will be floated as an inquiry for the respective vendors, and the vendors will give the offers, and those offers will be evaluated. So that is the second phase after the engineering, that is the procurement phase. So procurement phase, floating the inquiries, then vendor offers will be evaluated, and then vendors will be technically evaluated, and then commercially, techno-commercial discussion, negotiation. Vendor negotiation is nothing but it is nothing but techno-commercial negotiation with them. And then once you find that one of the vendors is suitable for me as per my quality requirement, technical requirement and quality, and of course the price, then they will give the order. Then vendor approval will be there, and then they will give the order, and then vendor will start manufacturing. During this phase, they will give vendor documents for review to the respective disciplines. And this is the procurement phase. So EP we have covered. Now the last phase is the construction. So site people start erecting based on the drawings which will be prepared by each discipline. Like by, for example, civil people have made some sort of foundation for the tanks. So they will start making the topographic, as per topographical survey, they will start making the leveling of the ground, and they will start making the foundation for the tank, for the pipe rack, for the equipment to be installed on that one. So those things will be detailed erection or construction drawings will be given by respective disciplines. Civil will give their drawings, piping will give, instrumentation, electrical people will give their drawings for the construction of, say, for example, MCC of substations, and instrumentation people will give the drawings for the construction of the control rooms. So this is a life cycle which we can say goes into three major cycles: engineering, procurement, and construction cycles. Now, if you go to the next one, then what will be the organization or organogram? So once we get an order as an EPC contractor, then we will have to do that. We have to form a team for the engineering phase, and some sort of people will be there, of course, for the non-engineering and construction people. For engineering, process engineers will be there, and control system engineers, and mechanical piping engineers, and then civil, instrumentation and electrical design engineers, and lead engineers and their teams, and then designers, AutoCAD or maybe modelers. For non-engineering project management, of course, this is a project, so we have to have the control of the project. So we have to have a project manager, and then under him, a project control team will be there, which will be monitoring the schedule of the project. The schedule is very, very important. It plays a very big role because the project, any project, will have to go through as per the schedule, and the different milestones has to be covered or will be executed in that project specific time frame. You cannot go unlimited with unlimited time, and you cannot give them unlimited time so that they can do their own, and they cannot take time as per their desire. So there will be a project schedule that I will show in the next slides. So project management, project manager will be there, and project control engineer will be there. Under him, a planner will be there, and administration engineering administration and procurement department will be there. And of course, automation and quality control administration will be there, and accounting for commercial activity. And at the site, they will have an office, maybe at a later date, or in the beginning for the topographic survey for civil works actually. And the field management will be there, that will be covered at that place where you have to construct the site. So this is the organization. So kickoff meeting, we generally, once the order is given to the EPC contractor from the owner, then they will say, okay, we will have a kickoff meeting. So kickoff meeting will have to have this presentation, and we have to say that hey guys, we are having this team. These teams will cover the entire phases of the projects, and these are all eligible persons. So we have to share their CVs, and then maybe they will just discuss with them their understanding and everything. Lead engineer especially will be involved in this one, and then they will take their uh, understanding. They will understand that okay, the EPC conductor knows what we want, and then that starts with the kickoff meeting, and the project schedule starts with that one. And then there's nothing but this is only a realization organizations, engineering, procurement, construction, and commissioning, and project control and quality control. Of course, I said once the order is given to the vendors, and then the panels or something, some equipment are being manufactured over there. So they have to, quality people will have to go there and check it, and then give the dispatch clearance. And then the HSE safety engineers are also required, and other project services are involved into this one. Now, if we see the discipline, various disciplines are involved, as you say, as you can see that one. So yeah, under project, we will have engineering, procurement, and construction teams, and then I will just focus on the engineering first. So engineering will have different disciplines, instrumentation and control, and then layout and piping people will be there, and process engineers for the preparation of PP and ADs, and then electrical people, those who will make the single line diagrams, or the basic design of substations or MCCs will be done by them. And then equipment, static equipment and rotating equipment, these are all mechanical people actually, and the piping engineers. And then civil, and of course HSC safety, means it's not about the safety of the person, but it is about like fire and gas and firefighting systems will be required for an oil and gas industry, or any hazardous areas. So where in case of any fire occurs, the foam or fire porers will be there. So those things will be designed by these people with the addition of the fire water tanks, and then fire water pumps, and then they will ensure that the entire plant, in case of an emergency, or in case of a fire occurs, then those things can be means utilized, and the fire can be extinguished in the right time, and before it propagates into other areas. So these are the various engineering disciplines, and which will have their own role. Now we will go to EPC's next phase, that is the workflow. So how a workflow means, after getting the order of kickoff meeting and all those things, all these people will sit together, and they will concentrate on their workflow. So the planning person here plays a big role, which comes under project control. So project control engineer, a planning engineer, in a primary or Excel sheet, they will make a schedule with, of course, with concurrence with all lead engineers, and they will say that these are the major milestones. So they will make the schedule, project schedule, in first phase, what will happen, who will give which document, which drawing, and then what are the required documents or drawing prerequisite for me or any other discipline engineer to go ahead. For example, instrumentation guys or piping guy needs PNIDs. So process engineer will go for preparation of PNID based on the process flow diagram. So they will do their software, they will use their softwares, and they will go for process calculations and process parameters they will decide. And in a, for example, in a pipeline, what will be the pressure, what will be the temperature, what will be the flow. So those things, and what are the major instruments required for there to be installed, and what are the major valves to control the plant. So those things will be, before going ahead, we have to have a schedule to control the project. So here level 1, level 2, level 3, level 4 schedules will be made in a different manner. So first they will make a level 1, a broad, for example, 12 months it will have a span, and first 3 months we will have engineering, next 3 months we will have procurement, next 3 months we will start erection and commissioning, and the last 3 months we can say we will go for commissioning. So this is the level 1. So that then level 1 will be again expanded and will be explored in a detailed manner, and then level 2, level 3, level 4. So the basic idea is to have a level 4 with us, with engineering team. Then they can go ahead with all the required dates or deadlines to be adhere or to monitor during the different phases of the project. So here engineering involves varieties of specialists which include process. All these engineers will be involved in making the level 4 schedule, which will be developed by planning engineer. The process engineer work to produce the required deliverable depends on not only within the functional discipline itself, but also among the process mechanic. So for, as I said, for making a, a foundation for example, for making a foundation of a tank, a civil engineer will say, I need the data from the static engineer, what will be the load coming on that soil. So based on that one, he will start making the drawing so that the foundation can be made. For example, a foundation has to be made for the compressor. Then they will say that, okay, I need the compressor data. Compressor, what will be the size of this compressor? So all these things will be decided by initially by the process engineer, and then it will be given to respective discipline, static or rotating engineer. They will estimate based on the required pressure, what will be the compressor size, for example. Say for example, I need 12 bar pressure in the plant. Then what will, and the consumption of complete flow and volume, how much volume of this one fluid will be required. So then they will say these are the tanks which will be required, this is the diameter of the tank, and this is the height of the tank, and based on that one, this will be the load exerted on that ground. So based on that one, a civil engineer can have the understanding and he will start working. So these are the things which we need to understand in the basic flow. So there the involvement was of every lead engineer in consultation with planning engineer. So planning engineer was those things. So here in this phase, interdependency is, as I said, is a very major part. So we are depending on others. So it's, we can say, we have a beautiful line, that one, that we are internal customers to each other. So though the customer is our end client, but we as an engineering interdisciplinary lead engineers are teams or having inter customers, means as process engineer will produce the PNID that will be used by piping engineer or instrumentation engineer. So we are the clients for them. So we will demand them, I need the PNID in this format, in this style, in this fashion. So until unless he gives me those inputs, or piping engineer, he cannot make the MTO or material takeoff, or he cannot make the estimation or BOQ for the pipelines. So until unless those things are not done in a proper way, you cannot. So for instance, instant piping routing drawings are issued after the process diagram. It is defined in that one. The sequence of engineering phases are defined in those things. So once those things are there, then we will say that, okay, we will which document or which drawing we will give for review of the client, or for approval, or for construction. All our comments issued for approval, issued for design, issued for construction, all these things will be decided based on those requirement and type of the document only. For example, a PNID will be issued for review, issued for comments, or issued for design, issued for review, and then IFC also based on that one. An isometric will be issued for construction also in the end. But for example, a data sheet will be issued for design, issued for review, issued for design, issued for approval. No need of issue for construction, because that will be given an order to the vendor and then they will do that one. So these are the things which we define in a document index. So the document index is nothing but a list of the document or drawings which we will deliver from the respective disciplines. So those things will have in front of that drawing. We will say issued for review or issued for construction, like that. And then the same thing I have just gone in a better way. So here we can see the entire strategy is dependent on engineering procurement providing the deliverable to meet the path for construction. So our aim is to have a complete understanding of a construction engineer. He should have a drawing in his hand, or he should have everything. He should have a GA, he should have a drawing, he should know what is the pressure, what is the temperature in this pipeline, and how he has to handle all these. So our focus is to facilitate all these, through all these phases in procurement, that he can have the equipment, right equipment, to erect and install at the site. So this is our focus. So we can say engineering forecast for IFC and engineering work packages. All these things will be required for the construction people. And now, if we start making or working, preparing the deliverables, making as per the document content index. So we have a list of documents or drawings, and we have a timeline, and we know that we have to deliver within 15 days this drawing or that drawing, and the next that drawing will come from other discipline, and then I have to start making the other drawing. So this is just a simple, I just to try to explain this one. This is a simple engineering discipline workflow. So for example, process engineer will make the diagrams, PNADs, process flow diagrams, and do the calculations, process flow or process this one process data they will give it to me, or a mechanical data they will give it to the constructor, to the mechanical people. So this is the thing they will do in the beginning. So maybe after this, in first phase, their role becomes lesser. Then civil will be doing geographical drawings, will be making the topographical survey drawings and all those things, and they will do certain calculations. The static load what will have on that soil based on the inputs given by the process or mechanical engineers. So these people, civil and mechanical, will do the calculations, and the piping people will also involve in geographical drawing survey and along with civil, and electrical also, an instrumentation people, because the location is important for me. The control room should be located away from the hazardous area, for example. Then it is my duty to ensure that geographically the things are rightly, or the buildings are rightly placed in the beginning itself. At the latter date, I cannot say, hey guy, I cannot take the cable from here because the tank is coming in between. So I have to, means instrumentation, from instrumentation electrical perspective also, we have to involve ourselves in the geographical drawings or the layouts. And then, of course, the diagrams or drawings will be prepared by instrumentation electrical people, and architecture, civil architecture people will start making the drawings for the substation or MCC or the control rooms. And of course, the calculations will be done by not only by the process and civil, but mechanical, piping, electrical, and of course, instrumentation also does calculation, Instrucal. But that will be preliminary calculations which will be done in the preliminary stages, and for the safety wall and other control wall and other inline instruments, and then we will give it to the vendor, and then vendor will give those things back to us. And then equipment or material specification data sheet, which will be prepared by generally mechanical, piping, electrical, and instrumentation. So these are the things which we need to prepare a data sheet or material requisition, so that we can float the inquiry and the vendor can understand exactly what type of equipment or what type of device or instrument we need to procure from them. And of course, site people will be having the civil inputs, from civil, from piping, from electrical, from instrumentation, and from mechanical also, of course. So this is a workflow which is depending on different documents and different activities with different disciplines. And project execution, the same thing. This will be a displayed which will be followed. This is the workflow diagram which will be followed by the disciplines at the different stages. Inputs for the engineering and 3D modeling they will start doing, and all those things. And if you see this face, these faces, this is generally an input for the 3D model, but depends upon a complete engineering different phases. So here, if you see 30% model review, 60% and 90%. So now, what is this model actually? Nowadays, what we are doing, earlier in the olden days, people used to make the data sheet and get layout drawings and then give it to the construction people, but the construction people were not having three-dimensional drawings. So there were chances that they could do mistakes or they could not understand. So in these maybe 15 to 20 years, the era has started that people started having their three-dimensional drawings. So 3D models are being prepared nowadays, and then 3D models are useful for better understanding for everybody, for us as well as for the construction site people. The tanks and all those things will be shown in that one, and pipe racks and cable tray routing, cable trays will be modeled onto that one, and the clashes and all those things. So during these modeling, so we have to have a, a meeting, or we should review these at different stages. So generally we call it 30% model review and 60% and 90% model review. So in the beginning, only geographical layout will be just prepared, and then a broader perspective, broader major pipe routings will be shown. And then 60% model will be just precisely detailed. And then in 90% model, maybe more detailed. So in the end, you will have every small pipeline, every small instrument or device will be shown into that one, and every cable tray. So this is a project execution from the perspective of the 3D modeling. So there are different software used nowadays, E3D or PDMS, PDS, and many piping design software. Generally, these are the piping design software and tech law. So the civil and both can be combined and all those things. So civil and piping people will show, and along with instrumentation and electrical designers and modelers. So in the end, you can see, or you can visualize, or you can see the complete plant in a 3D fashion. So we can check, means cable tray, my cable tray, electrical cable tray, instrumentation cable tray is having the different required gaps or not, or it is not clashing, or nothing is left and it is not having any obstruction. So the tanks and all those things are placed properly. So that will give means a better understanding for everybody, especially to the construction people. And then the purpose of issuance, as I said in the beginning, that we will have a deliverable list which will have a complete in document list of documents or drawings to be prepared for each discipline, and the purpose issued for design or issued for review. So those are the things already decided there. So this is the sequence, we can say, which are being followed, or it is a flow for issued for review, issued for design, issued for approval. These are the different phases, and issued for construction, it is for procurement, and then procurement support, and in the end it will go to the site. So it will be the responsibility of lead engineer to submit all these drawings at different phases, and then once, if any comments are coming, and then we have to incorporate. But before issuing these drawings, we generally will have internal review. So every, as per quality, as per ISA quality procedures, now we should have signatures of three persons. A person who is making the drawing or document will have to check, self-checking, then he has to sign on that one checklist, and then a person who is reviewing that one, he has to do, and then a person who is approving that one. So generally, a designer or engineer will make the drawing or document, and he will self-check and he will sign it that I have checked everything, and then he will go to the senior engineer or senior, and then he will check and he will say okay, it is okay, or he will return it and he will ask some corrections, and then the third person is final approval. So once it is approved internally, it will be issued to the client, or maybe in some cases, PMC will be their project management consultancy. Some sort of people, some sort of customers will hire some agencies, a government or private agencies, like for example in India, PDL and other agencies are there, and in Gulf, in other places, project design from is constituted by the customer will be there, and those people will be reviewing the document and they will be commenting, because they will have to have a monitor, a person who can check it. So if you don't have check and balance, then the design team can do mistakes, and then that may lead to a big problem. So these are the different phases of any deliverable and the issuance purposes. So this is a, a flow diagram which leads to our execution and the issuing purpose of every document and drawing can be said here. And next we can go for the next phase, engineering phase. So as I said, once we have to start working on any EPC project, then scope of work we should understand, and then generally we will prepare design basis of our own. Each discipline lead engineer will prepare a design basis on what ground they are going to design it. Sometimes it will be given by the client, sometimes we have to make it. If it is in the basic engineering, we have to make it. If it is detail engineering, then it will be given by the client. So if it is given by the client, then we have to adhere. For example, I have to make a datasheet for pressure transmitter. The client says the output should be 4 to 20 milliamps hard. Then I have to ensure that this is done, this is covered in my data sheet. If it is written that it should be foundation fill bus, then I have to remove the 4 milliamps and that hard, and I have to ensure that foundation fill bus output is not mentioned over there. For example, the gland sizes in every project, if it is in metric M20 or M40, then I have to go for that one. And if it says that in that project it is should be in inches, then I have to go for the inches size. So these are the things which we need to design. And in one of the projects in Apollo or somewhere, I think for the moon project, the Russians and Americans, they were collaborating, and they were going with inches, and these people were going in and then at the end the project collapsed. And then when they did the inquiry, one team was following metric, one team was following FPS system, so CGS and FPS. So we need to have complete design basis for each discipline. So sometimes it will be given by the client, sometimes we have to prepare. So this is a very important document prepared by every discipline in the beginning. And I will just focus now from this slide, I will focus on the instrumentation engineering. Like for example, layouts will be prepared, will be given by the piping layout people, and I will start making cable block diagram. PNIDs are given by the process people, and I will start making the other index and then data sheet and other things, and then I'll prepare the MR and all those things. So this is a detailed phase of complete engineering which an instrumentation engineer or engineering team will go through, will make complete deliverables based on these inputs or outputs. So these are the different phases inputs. For example, PNID, if it comes, and then piping layout comes, then I can make the cable block diagram. With the help of cable block diagram, I can go for interconnection diagram, instrument JB, cable routing. I'll show all these examples. So since this one is a demo class, so I'm just going very, very quickly because I have to cover in 1 hour complete all these disciplinary ways, as well as I'll focus on instrumentation. So these are the different phases. And package vendor instrument, if you see on the right side, and process data sheet, sizing calculation will comes for me to make the process data or specifications or data sheets, and then I will use it as an input for the material requisition, and then floating as an inquiry, and technical bid evaluation TBs, and preparing of PR or purchase requisitions will be done. And not only for the field instruments, for the DCS and other input, then I will take the PNID and do the IO counts, and then I can make the DCS and ELD control system specification with along with the input output counts. So here in instrumentation engineering, from that perspective, the IO count will be taken out from the PNID. So we'll cover one of the sections for the PNID, and there I'll show how to pick up the IO count and then make the specification, and those specification plus IO count will size my DCS or ESD or PLC. So that depends upon that one, and then what will be the sizes on those things we can estimate. So this is about the datasheet preparation and material requisition and IO count picking up from the PNIDs, and then layout and drawings and cable routings, cable schedule, all those things are covered over here. So finally MTO, and then all these things will be given to the construction people, control room layout and all those things. So these are the different phases of. And once we we are making all those documents or drawings, and then we will floating as an inquiry or giving it to the different departments. So then we can say these are the various phases of, or we can say this is the cycle of complete engineering and then procurement and other things. So if I have to give certain document to different disciplines, so we can say interdisciplinary check. So interdisciplinary check will also play a big role, and it should issued for review, issued for approval, depends upon that one. If for example, if I have to make a data sheet for the level transmitter to be mounted on a tank, then I need the tank GADs from the static engineer. I need the tank height. I need the process data of that tank, the fluid parameters, so that I can select an appropriate instrument. And then, for example, if guided radar, what will be the guide of what will be the length of the guided wave, that wire. So all these things are very much important for me to make it. So it is interdisciplinary, means interdependent, as I said in the beginning, that each discipline team is depending on others. Sometimes once those inputs are arrived to them, then only they can go ahead. And based on assumptions, sometimes we do, but at a later date we have to do the corrections. So for example, one more example I'll give. The tank, on the tank I have to do the design of one level transmitter. So I have to ask to the static people what will be the size of the flange, 2-inch or 8-inch flange. And if any isolation wall is coming, and then wall piping will take that isolation wall, so I have to ask them what is the size of your wall and what is the end connection of that wall, so that I can put it in my data sheet and float as an inquiry, so that the vendor can give me proper interface or proper compatible instrument, so that once it goes to the site, it should be properly installed. So this is our focus on that one. So the cycle is basically on that one. And then, as I said, it is again the same thing which I was telling in the beginning, that process people will do the preparation of PFDs, process flow diagram. They nowadays they are using some sort of softwares, and then heat mass balance calculations they do. These are all chemical engineers, process engineers basically. So in the beginning, they will take those only the parameters from the client, that they will say, okay, client will say, for example, I need to take the propane and butane from the ship, and this is the temperature which will be well, minus 42 and minus 6 is the temperature respectively for propane and butane, and it will coming from the jetty, and it will be going to the layout of the to the plant of 4 kilometers. Then they will have to have the complete understanding of the site, and then they will start making the preliminary process flow diagram. What will be the pressure, temperature and flow in that particular pipe, and based on that, what will be the size of the pipe, and what will be the size of the vessel or tank, and what other equipments like compressor or any other heat exchanger will be coming in between. So this is the beginning thing which will be done by any team. Means we have to first wait for the process engineer to make the PFDs, and then based on the PFDs, process flow diagrams and heat mass balance, they will prepare the PNIDs, and those PNIDs will be given as an input to the piping people, so that they can start making their documentation, because they know the line size, they know the piping material, and they know the temperature and pressure, and they can design their pipeline. And for example, as an instrumentation engineer, I can take those data and process data and I can make the data sheet for a pressure transmitter, which will be mounted on that pipeline. So PFDs and PNIDs will be prepared by them, and then PFDs and all PNIDs will be going to the rotating engineer for the for any rotating compressor, or maybe any other rotating equipment, pumps or any other things. And then pressure vessels, which will be a static engineer will be doing all those things. So pressure vessels will be used by static engineer, and then they will make the vessels based on the ASME section 5, section 8, all these standards will come into picture at a later date. By the respective discipline, they will have to follow those standards. And heat exchangers, for example, those are the equipments. And then the yeah. So these are the things which are interdisciplinary, means interdependent from various disciplines. So rotating engineer, static engineer, and heat exchanger, equipment engineer, everybody, owners, package equipment engineers will make all these things based on the PFDs and PNIDs. Of course, process data will be also there, and equipment specifications will also be prepared, and then it will be given to the vendor, and then order will be given, and the vendor drawings will be based on that one. So once vendor drawing comes, that will be the final GAD, for example. In the preliminary stage, the process will say this will be the size of your compressor. But once the rotating engineer will do the detail engineering, he will just check it, and then he will increase or decrease that one, and then it will be given to the vendor, and then vendor can again check based on their calculations, and then he can come back, hey, why you have done wrong, and then this will be the size, the smaller or bigger. So then that will be an input to the other displays as well as for the construction people. So this is, we can say, the one of the phases of that one. Then the piping engineer. So once the process engineer has done the PFDs and the PNIDs, then piping engineer will take those drawings or documents, and then they'll start making the plot plan, and then piping line diagram and PMS, piping material specifications, and then 3D modeling they will start doing, and then isometric drawings they will start making, and then they will do the stress calculations and all those things, and they will be giving all these drawing at different stages. For example, plot plan issued for review as per the PNID, and then piping studies and layouts, it will be issued for design, and then issued for construction at the end in the bottom. So these are the activities which will be done by piping engineers. And of course, the interdependency is there. As I said, process flow diagram and PNIDs are given by process. So those are the inputs for the piping engineer to do their detail engineering. And of course, they may ask instrument engineer also for inline instrument. For example, a valve is coming. In the beginning, instrumentation engineer will have to have some standard, as per international standards, a 4-inch wall, a control wall, or type of the wall is, if you mention it, and then there are software, then that will give the dimension, face-to-face dimension. So they will take those preliminary dimension, and they will put that one, okay, this wall will come in this pipeline, and this will be the pipe length and all those things, and then I can turn from here. But at the end, if the wall vendor document gives me, then I will give it to him, and they'll say, oh yeah, this is the final vendor drawing. So they will do the correction in their model and then in their isometric. So isometric is nothing but the pipeline where it comes and how it goes, elevation and all those things. It elevates or it comes down, all those things. So these are the things which will be done by piping engineering discipline. So process we have seen, and piping engineering discipline engineers activities we have seen. And of course, 3D modeling, as I said, PDMS is a software. And if you see here, there are the 3 phases of modeling. So piping engineer, not only piping, but civil and instrumentation electrical modelers, they will start working parallelly, and they will not work in isolation, not work in silos, but they will have interactions with each other, and as a team, they will start making modeling the complete plant. And then in the initial stages, as I said, in a 30% stage, so a 30% model, a broader model as per the plot plan, will be shown to the client, and client will suggest, no, the road should be here, and then you take the road out from here, and then no, we should not have done here, and then tank we just, generally those major equipment they will not ask, but the cable routing, I mean, they may ask, and then cable NT they may ask, no, I don't want from north side, I want it from the east side. So we have to do the corrections and that one. So whatever the comments they give, and then we have to close that one, and then next stage, 60%, at the next stage of the project, we will execute those comments, and we will do more modeling, and then we go back to them and we will show them. So this will be a bigger session actually than previous session, and it will be much more detailed. And in the end, 90% model reviews. So this will be the final and fine-tuned and everything. In this case, all JVs will be shown, all instruments, PT, pressure transmitter, where it is coming, and how the cable, every cable, every JB, every for example, a pump is there for electrical, this one from electrical or mechanical. Then LPBS, local pump, local push button station, where it will come. And all these things should not have obstruction for the person who are working on that one. So for example, if you see the model, then from that perspective, safety perspective also, and everything, like for example, if it is a pump house, then they should have a room or place so that a pump can be brought, a bigger pump can be brought by a crane or something, and that can be replaced during maintenance, maybe after 2 years or 5 years. So those aspects are also to be taken care, and platforms and then railings and all those stairs to be provided for the wall operation. So wherever the stairs are not there, they will say that then we need the stairs, and all those means accessibility we say. So from all the perspective, from the accessibility, from the operational, and from the construction point of view, and specifically especially for the maintenance people, we should have a complete room for the people who, those who are doing maintenance in future. And of course, in the last not the least, but we have to have a safe evacuation. If any area, if any pump house is there, in case of any fire, or if any untoward incident occurs, the person, those who are working there, should have a safe escape. So while running back, he should not have a pipeline in between, and then he should not fall down, and he should not get stuck over there. So these are the things which will be taken care during these phases of the complete 3D model. So skid modeling, I have just given an example, but the skid is more critical. That's what we have to take care more, because that will be given in a specified plot, and then you have to play complete, you have to make different levels and different floors, and then we have to have complete by equipment shown into that one. It will be very congested, but at the same time we should have accessibility and states and all those things, and every cable, every pipeline should be routed, and the underground, above ground, and all those things to be taken care. For example, the trench is passed, is shown by electrical people. It should not fall with the foundation of a pillar, and pillar's foundation will be in depth in the soil. And then if both people are working in an isolation, then electrical engineer will show his underground cable route, and maybe some drainage is coming on that one, some under means underground pipe is coming and obstructing that one at the site, and then they cannot do the construction. So these are the things which should be taken care during this complete review. This is a very important nowadays 3D model review. So engineering workflow, once again, a recap of that one, that process, piping and mechanical engineers, how they go with their this one process flow schematic, and then process study will be there, process data sheet will be prepared by the process engineers, and process engineering flow issued for approval, and then all these things coming for other disciplines, engineering data, and then they will be making the requisition for equipment, and then vendor inquiry, like a material requisition will be issued, and the technical bid evaluation will be done after receipt of the offers. So once you are giving a material requisition as an inquiry, float as an inquiry, then the offer comes. For example, for me, a DCS vendor will give an offer that this is the DCS, this is the PLC as per your account. A pressure transmitter vendor, Honeywell, will give me data sheet of 5 number of pressure transmitters which I have mentioned as per the process data. So then I have to review that one, and then technical evaluation I have to do. So like this, all these three disciplines, just as an example, I have shown process, piping, and mechanical engineering. And of course, piping routing and piping general arrangement, GAD, is all interdiscipline, because walls, inline instruments, we have to give them. And then by giving flexibility study and loading, those stress calculations and all those things they will do. And then pipe supports they will do, and pipe supports, and all the tray supports, all are also important. And then MTO, material takeoff, for every size of even 1 inch pipe also will be counted. It will not be left uncounted. Every item has to be counted from every discipline. So we can say here one color we have given for process, and one is for piping and mechanical, but more or less the same thing which goes through every discipline, but they have their own cycle and their own set of drawings and their own point of view. But interdisciplinary interdependency is always there. Of course, their aim is to procure, for example, process is not procuring anything, but piping is procuring their pipes, or maybe their elbows, or maybe their equipment. And then mechanical engineers will be procuring their equipment like static tanks and all the vessels, or maybe the compressor or DG set, or maybe any other equipment, rotating equipment, or pumps and all those things. So if a pump has to be, I mean, pump data sheet has to be prepared, then they have to give it to electrical engineer so that the electrical part can be filled by them. And mechanical engineer will see that this will pump at this pressure, this is the head pressure and all those things, and this will be the size, and this will be the type of the centrifugal pump, for example, it is a centrifugal pump or what other type. And then based on that one, the electrical will give the load and all, and the voltage requirement and the wattage will be taken care. From instrumentation point of view, I have to say that okay, I have to give a command to that pump MCC in the pump, so that the pump can be controlled from the control room. So if you see, it is a good example of a pump. It is procured, then a mechanical rotating engineer will have to involve, and then electrical engineer also will have to see the data sheet. And then of course I have to see from instrumentation point of view whether anything, any vibration sensors or temperature for bearing and all those things are being given by the vendor. Then I have to have a cable for that one, bearing temperature or binding temperature or any other thing. I can not leave that one, it is not my job. But as a complete package we have to see for, so it, from every perspective. So every item will be checked for all disciplines, respective disciplines, we can say. So we say that interdisciplinary check IDC. So this is just an example of workflow for the piping and other disciplines. So piping preparation of piping layout, 3D modeling and design calculation they will do, and then technical specification, and then piping material specification they will prepare. VMS is nothing but wall material specification. So PMS, piping material specification, VMS they will prepare, and then route survey layout they will do, and alignment sheet they will make it for the pipelines, and then they will make the MR for all these equipments, and then they will float as an inquiry, and then offers come, then technical bid evaluation TV will be done. And then once the order is given, then the vendor, the data or vendor documents will be checked by them. And then development of detailed piping drawing, all these things like isometrics and GAs, all these things will be prepared, and then at the end they will come up with a bill of quantities or BOM or MTO. And in the end, a stress analysis report they will submit it to the client that it will work smoothly. If for example, if any pipeline is there, because of the laminar flow or turbulent flow, it will not have any vibrations or anything. Enough supports are given at equal intervals and all those things, that will not fall down because of the static load and all those things. So these are the different deliverables prepared and submitted by the piping engineer. Now for example, mechanical engineers, here we can say mechanical, like for example, equipment drawings and data sheet they will prepare in the specification. And then heat transfer, like for example, it can be anything. It can be from minus temperature to ambient temperature, or maybe from ambient temperature to some sort of higher temperatures, like so for example, boilers and all those things. So heat exchangers and all those things, fired heaters, like for example, oil fired or gas fired or furnaces and all those things. So these people will make the data sheet and all those things, which, and all these things, if it is in, it is required as per the PNIDs, of course. And then preparation of data sheet for all these rotating equipments and pressure vessels. As I said, pressure vessels are also very important, because the pressure vessel is, if it is like for example LPG gas cylinder which we use in our houses, then it will have 15 or 16 bar pressure. Then that metallurgy and that cylinder should have that complete capacity to contain that volume and that pressure and the temperature, or maybe the ambient variations will have an impact on its internal pressure, and it should not get blasted during transfer or during storing, or maybe during use. For example, if it is used in hot environment in the desert, if it, for example, if somebody is cooking, then that LPG cylinder should not get blasted over there. And if it is being used in in Russia, for example, if it is -40, then that also should be stand over there. And depending upon the various ambient temperature variations, the internal temperature and pressure should not have an impact on the body of that vessel. So this is a very, very important. ASME section 5, section 8, they will see those standards. And API 650, 620, and all those things. As I said here, yeah, it is written here, ASME section 8, division 1 and 2. So these are the things looked out by the mechanical people. But as an instrumentation engineer, we should have like preliminary knowledge. Like basically, I am an instrumentation engineer, but I have the basic knowledge about that one. But maybe broadly, I don't know much, but I can say that these are the things which will be done by them. And then fabrication detail drawing and including bill of quantities and all those things, data sheet they will prepare, and the preparation of MR and TB and all vendor follow up vendor document. And then so this is again the same workflow for them. At the end, everybody will make the data sheet and specification, we make the material acquisition and get the offers, and they do the technical evaluation. And once the order is given, and do the vendor data review. But they have their own document, they have their own data sheet, they have their own perspective, their own aim to purchase their own required discipline items. So this is engineering workflow for a mechanical engineer. And then from the civil perspective, civil engineer will make the structural general engineering drawings and the civil foundation design for example, for the buildings, for the pipe racks, and for the other tank foundations, and maybe compressor foundation, or maybe diesel generator set, maybe MCC building, many things. So they will have to prepare those things, the civil architecture layouts and blast designs of buildings. So this is a very crucial point nowadays. So sometimes the client will ask for the control room to be designed for the blast proof, and we have done one project for advanced water reactor that was done by BARC, actually, Bobet Analysis Center, designed by them. It was a table concept, and then we have done that engineering. So there we were supposed to make the control room blast proof, because it is controlling the advanced water reactor. So it will have seismic, like for example, it will have to withstand a huge earthquake. You can imagine that if any huge earthquake, maybe 8 or 9 on Richter scale, if it comes, then that building should not have any cracks. So blast proof is nothing but that one. So some buildings are to be designed for blast proof. And those are crucial. And then structural calculation they will do, analysis they will do, and wheel calculations and all those things they will do here. And then the structural steel jackets, mooring, and this mooring is nothing but for the offshore plant and the jetty and all those things. And loading equipment, marine loading arm, and marine unloading arm, all those things will come on under here. And then of course lifting analysis, if any equipment is prepared in the workshop, and then it should have the lifting hooks and all those things. It should means the required crane capacity also they have to mention it. And of course bill of quantity at the end, as every other discipline is doing, they have to make the MTO or bill of quantity, so that everything should be covered in that table. And then every small to big item should be covered with all units of measure, quantity or maybe meters for everything. And then bar bending schedule, structural detail drawing, and shop fabrication drawing they will prepare as per their requirement. So this is one thing. And then once we go ahead, so process, as I said, will have the initial role. So once again, I'm just covering, because in the beginning I just covered without a slide in the beginning stages. So I'll just go with more detail here. So simulation study report. So they will have a software. So as I said in the beginning, if any client has done their own basic engineering, then they don't need, but they have to do the verification of that one. But if the basic engineering is not done, or front-end engineering and design feed is not done, then they have to do the basic from the scratch. So basic engineering is generally done by process and civil and piping. So process engineer will have to make the software, and then equipment broadly, equipment sizing, pipeline sizing, and all those things. They have to do the calculations, hydraulic calculations, and heat mass balance calculations. All those things they have to do. So equipment sizing will come out with this one. Tank, what will be the tank size? What will be the compressor, or what will be the certain equipment, flash gas compressor, for example, or maybe instrumentation compressor, what will be the size, or maybe cooling tower, what will be the size of the cooling tower, all those things. They will decide a preliminary study, and based on their process data required. For example, I need to have this much of flow or this much of input I am getting The input process fluid is having this parameter, this much pressure and temperature, and output after processing will be the output. This is the different fluid, and this will be the parameters of temperature, pressure. So in between all these equipment to be placed or pipeline to be routed on those things, but that will be decided based on these people, the process and HSC. HSC plays a big role for making the firefighting equipment. For example, the tank is there, then fire water is required in case of any fire occurs in the tank or on the roof of the tank. So on the roof, foam pourer will be there, or maybe immediately means the fire should be extinguished within 10 seconds, within 5 seconds, otherwise it will propagate. And in case if the tank is already catching fire and it's totally caught fire, and then the tank should be like how do we take the shower? So the tank should be given a shower of water. So all these sprinklers and all those things will be designed, and hydrants and all those things, firefighting equipment will be designed by these people, HSE. So process engineer, a chemical engineer, again a chemical engineer can become an HSE, health and safety engineer, but actually here they will be doing all those safety equipment, firefighting equipment, and like hydrants and fire water equipment, fire water tank they will design, and fire water pump house, and like jockey pump and like diesel pump. And in case of even power failure, they will ensure that diesel pumps are there so that they will give the firefighting people the enough pressure of water to extinguish the fire. So process engineer and safety engineers will do all these things on process data sheet and line sizing calculation, heat exchange, and then of course the firefighting equipment. And then again the process engineer will give the control wall calculations. For instance, an instrumentation engineer, they will give the process data sheet, they will give the control wall coefficient of wall. We will see once we go for a different session for instrumentation sizing and all those things. So those things will be given preliminary by them, control calculation, what will be the CV and all those things. And of course, thermal safety or temperature controller or pressure controller or pressure safety wall data sheets, and all those sizing, safety wall sizings they will do, and they will give us the data completely so that we can include in our data sheet and we can upload as an inquiry. And of course, in the end, these two engineers, along with instrumentation engineer, will have to participate in various studies. That is the last line, hazardous operability. So in case if any plant is designed, then a team will be constituted, an expert will be constituted from outside and has of chairman. He will study the PNIDs and he will see the operability, and then he will ensure that everything is all equipment, all safety precautions are being taken. For example, he will say that okay, in this pipeline, if excess flow comes, spurious flow, or no flow, or less flow, or high temperature, or low temperature, then what happens? The pipe should not get contracted, the pipe should not get expanded, the pipe should not get exploded. On those all those things, he will see the scenarios, different scenarios, and thus that study is called hazardous operability, HAZOP. So HAZOP study will be done by definitely an external expert, a chairman, but will be participated by process and safety and instrumentation. Mainly these engineers will sit together, and the design team will have to say to the chairman, as a chairman, that okay, my PNID and my design is safe, and in any condition this will have a protection. For example, he will say what happens if pressure goes high in this pipeline, then he will say that okay, pressure gauge is there, pressure for local, for pressure transmitter is there, which will be giving indication in the control room via SCADA. And if it becomes high, I'm going to close this wall, I'm going to close this pump, so stop this pump. And in case if this wall does not close, then what happens? He will say, then I will say that okay, another wall is there, or another thing is there, or after 10 seconds, if it starts building up the pressure, then I will close the pump. So those are the things. So DCS and ESD will come into picture, all those things. So these are the things which will be studied over there. And if it recommends any other instrumentation or any other wall to be added, or generally not deleted, but generally they will ask to add safety wall. For example, the tank, if the tank is having any pressure inside the tank, then tank should not get blasted. He will say, then we will say that okay, level transmitter is there, and level transmitter and pressure transmitter is there, and pressure transmitter fails, level transmitter fails. Then we will say that okay, we have a safety wall, we have the emergency relief wall, we have the other devices which are mechanical, which will definitely work. So breather valve, so breathing will be done. So in the tank, it will be always the pressure will it will not be allowed, it will not be allowed to increase. So all those things we have to explain them, and then the complete team, if the complete like assembly, who those people are sitting over there, they are satisfied, then we can go ahead. Otherwise they will say that okay, you have to put one safety wall on the tank, or maybe one more breather wall, or maybe rupture disk you have to put it over there, or maybe a transmitter to be added, another transmitter, this fails. So these are the things which comes under hazard. Then hazard is again the same thing, hazardous identification and all those things. And then of course seal study, hazard and hazard is same thing actually, more or less, or slight difference. But safety integrity level, again the second study, which is a major second study. So here safety integrity level, if for example, if any transmitter fails, then another transmitter is there or not, and then probability of failure on demand or availability of the transmitter is ensured. If it is not there, then we have to put another transmitter, maybe another transmitter. So one out of three, two out of three, and all those things votings. And then for example, if three transmitters I have put, if one transmitter fails, another will say, and then another is there, and the third one is also there. But if the wall on which I am taking action, if it fails, if it is stuck, if it is not closed, when the demand comes, then I will be screwed, and then I will say that okay, I will have to have one more wall. So safety integrity level is again a study level only done on the instrumentation part. So then SIL 1, SIL 2, SIL 3 ratings will come for all the equipment which are reporting to ESD. This is applicable for the instruments or equipment which are reporting or which are controlled by ESD. So these are the various studies which will be participated by process and HSC engineers. And then of course, instrumentation engineers will be implementing all those things. And then electrical instrumentation, of course, electrical engineer will make the load list, power balance calculations, and the single line diagram, specification data sheets for their motors and other things. And then cable schedule they will prepare, and instrumentation also will prepare cable schedule. And of course, PNIDs instrumentation will involve for the symbologies and index and IO list and layouts and installations. All these things which will be covering in our detail this one. And then junction box termination diagram and all those things, substation and control substation will be done by the electrical people, and control design will be done in instrumentation, and of course in the end as built. And then of course here the software SP, electrical smart plant electrical and smart plant instrumentation softwares are being used apart from Word and Excel and other AutoCAD drawings. So in workflow for instrumentation, I think I am taking more time. Yeah. Is it okay? Hello? Okay. So now our focus is on instrumentation. So as I said, based on the PNIDs, we will make the instrument index and then IO list. We will pick up the instrument IOs, and then we'll make the data sheets, and then we'll prepare the hookup drawings so that the construction people can make use of that one, and then instrument loop diagrams, and then the connections can be done as per that one. And then instrument layout drawings, and all those will involve control room layout and instrument location layout and tray layouts and all those things. Then cable block diagram will prepare in the beginning, and then cable schedule and junction box schedule, and then junction box termination detail, and then of course instrument air required for the controller. So we make the drawings for that one, and the logic diagram based on the further. And then in the end, MQ or BOQ for the complete instrumentation items. And then workflow for instrumentation, I'll just go quickly. As I said, PFDs and PNIDs and other especially PNIDs are required for the instrument index, actually not much. And then this is nothing but a typical PNID, how it is there, and then process data which will be prepared by the process people and given to instrumentation people. I'll just go quickly on this one, and then of course this will be covering in the detail. This is a demo class of this. So all these things, how to read the PNID, how to make the index, and then IO list and all those things we will cover in the detail this one. So this is an index, typical index which will be prepared based on the PNIDs, and it will cover all the field and field instruments like pressure gauges, safety walls, and then walls, control walls, on-off walls, and pressure transmitters, and each row will have that one. And then what is the type of instrument, and on which PNID, and on which line it is coming, and then what is the output and input, and all those things. And of course, IO list will be only for the instrument, not for the pressure gauges or safety valve, but for the pressure transmitter, temperature like analyzers and all those things. So these are the things, the items which will be connected to the instrument via cable. So the instrument IO list will be only for the items which are electronic and which will be having cable and will be connected to the control system. So this is the IO list. So depending upon the type of equipment, like for example, if it's a switch, then we can say it is a DI. If it is a transmitter, it can be analog input. So if it is coming out from the PID control, from the control room, from the DCS or PLC, then it is analog output. So these are the types of DIDOs, AIAOs, which will be covered over here. And then IO list is there, and then instrument loop diagrams will prepare. It gives you clear picture, an instrument coming from the field via JB to the control room to marshalling, and then goes to the system cabinet, and will cover everything here, everything like up to the module and rack number, module number, and channel number. And then hookup drawings, which will be used by the construction people or installation people. A pressure transmitter will be connected, or differential pressure transmitter will be connected via impulse lines and various hookup materials. So this is a typical hookup drawing. And then layout diagrams, of course, control room, we have to make it in the preliminary stage in the beginning, and in the later on we have to correct it as per the vendor equipment. So vendor will give, in the beginning we will just do the estimation of the IO counts, and then based on that one we can say that these are the number of cabinets which may come over here, maybe two DCS marshalling cabinet, one system cabinet, or maybe one telecom cabinet, like that. So we can have a rack room layout and all those things. So, and these are the layout diagrams, field layout, and then layout, instrument location layout in the field where it is, AIT analysis instrument like a LIT level indicating transmitter is being shown over there. So where it will come in the different layout, it will be shown over there. And this is the typical cable schedule and JB schedule. A cable from transmitter coming to the JB and going to the control room, and then the JB schedule and the JB number and JB type, depending upon the type. And this one, the instrument like analog input or DI or DO, the type of JB will be decided. And then based on the causal effect which will be prepared with the process, we can have the logic, and logic will be built, which will be prepared in this diagram in this typical style, and it will be given to the vendor, so that the ladder and other functional block diagram logic can be developed, so that the PLC or DCS can execute the logic depending upon the IOs. And then of course, engineering workflow data sheet we have already covered in this one, and which will have line number, equipment number, and all those things will be there. And I'll just go quickly on this one data sheet. Once we do detail instrumentation, then I will cover what are the things to be taken care in this one in data sheet. So data sheet broadly will have data sheet in this one, in the tag number and all those things, and process condition and transmitter details, and then basic sensor element details. And then of course procurement workflow, as I said, data sheet will be given to the procurement people, and then they will get the offer, and then we will do the evaluation, and then order will be given. And then this is a typical schedule which will be prepared by planning people, project control people, in the beginning of the slides I told you, and in the beginning of the session. So this is a typical schedule. Interdependency is shown, and these are having the complete, like level 1, level 2, level 3, or level 4. Level 4 schedule looks like this, and it will have a complete plan to be executed of a specific time frame. You cannot have like a luxury to do endless engineering. And interdependency, those the lines are there which will be sent. For example, for making the rotation, I need the PNAD or plot plan, something like that. So work front will be there, which will be given for the site people, and IFC and isometric and all those things issued for construction drawing. So those things I will just skip it. And then of course the work phase planning, part of construction, and then these things will be done by the construction people. So I'll just wrap up in the end. So this is